Alrighty, so we've been talking about minimization lately, and minimization is going to be big. And just in general, optimization is really important when dealing with any function. So specifically, we're going to talk about Lagrange multipliers and how they can be visualized and perceived geometrically. So say you have a function f in terms of x and y, or it doesn't even have to be in terms of x, y, and originally, but being put in terms of x and y, and it needs to be minimized. What you can do with that function is you can set it equal to a series of constants and graph the resultant lines that are formed. And what you will end up getting is this like target or geographical map, like altitude lines appearing visualization. And these are the contour lines associated with the function, and they look a lot like a geographical altitude map. At each point on there, on the contour lines, when you have a perpendicular line, that is the represent the gradients at each individual point, and this becomes important when we add a constraint. So we're going to add a constraint g, x, y, and say that constraint is equal to 0. Now, it doesn't necessarily have to be equal to 0. It can be equal to a function in and of itself. But for now, we're going to pretend that it equals 0. And it will form this like a line intersecting through various points of our f function of these contour lines. So applying what we know, applying the fact that we know that these points that are perpendicular to both sets of lines are the gradients. And this is going to be the important one. There we go. Are the gradients. And these points where they intersect represent the points that are, I've lost my train of thought. The important part is the gradient. So at the point where we have the gradient of g of x that occupy a location where it is collinear of the point of f of x, we have an example of we have the minimization. And it doesn't have to be the same direction, the opposite direction, or it can be the same direction. It doesn't necessarily have to be a minimum, it can also be a maximum. But but it's important that they are collinear, that they are on the same quote unquote axis, this kind of line axis. There we go. So the function f of x in contour lines, at least, we can see as they slope down that they decrease and then increase, or decrease, increase, and then decrease, like the slopes themselves. And that's kind of where we get the concept of finding the minimization using these kind of contour lines, not contour lines, the gradient lines, in conjunction with the constraint function and the geographical altitude looking, I just lost the word, contour, that contour lines generated from the this function. And that is kind of the best way to visualize Lagrange multipliers and minimization using that form, is the point at which the constraining function and the original function have gradients that are collinear. You have optimization of some form, usually minimization.